Hi guys, and welcome to this first session of AS Chemistry. So in today's session, we're going to look at atomic structure and atomic models. So just a couple of quick things before we get started with content. In the Podia platform that you're using, you should be able to find a copy of the specification. So I'll break it down at each point so that you know what it is, which section that we're looking at. You should also have a sort of lesson overview so you know which sessions are coming next. I've put on their copies. I've put on their numbers of the textbook pages so that if you've got the recommended textbook, you can follow along to that. And you should also find a copy of the periodic table, because slight difference from GCSE that with our A-level periodic table, our numbers are a little bit more accurate. So our mass numbers, you can see there are lots of point something, because we've just got that little bit more accuracy at A-level than we did at GCSE. Okay, so in this session then, as I say, we're going to look at atomic structure and atomic models. So we're going to recap what the atomic structure looks like, just get back fresh in our minds about mass number and atomic number, how we can work out number of protons, neutrons, electrons. We're going to have a look at isotopes, how they are different from elements, how they vary to one another in terms of chemical and physical structure. And then we're going to look at the atomic models. So again, very similar to GCSE, looking at Dalton and Thomson's models. What is it that they did? What did they discover which changed our idea of the atomic model? To just be able to, appreciate that and understand how it's evolved over time. Okay, so structure of the atom then. Nothing really different from key stage 4 at this point. Protons and neutrons in that central nucleus of the atom, and the electrons orbiting in those shells. So those electrons are just orbiting around that nucleus. Obviously, we've got the positive pull of the protons and negative electrons, and therefore they're kind of holding them in place. Protons, neutrons, electrons, in terms of remembering their mass and their charge. Protons are positively charged, so that works quite well. Neutrons are neutral and our electrons are negative. The only slight difference you'll see now, again, because we've stepped it up a level, is that when we're talking about the relative mass of an electron, we now put that as 1/2000. So we just need that little bit more accuracy now that we've moved up into A-level. Okay, so mass number and atomic number, so allowing us to work out the number of protons, neutrons, and electrons that different elements have. Okay, so you might see a slightly different notation now. So when we're talking in general terms, we're using X for the element symbol, A for the mass number, and a Z for the proton number. So what we'll do is just have a quick recap of what these values tell us. So the mass number then, because if you go back and we think about the two that have got mass, protons and neutrons have got the majority of the mass. Electrons are so small that it doesn't really affect our calculations. So mass number is our protons plus neutrons. Squeeze that in. Yep. And our atomic, so proton number, so gives that away a little bit. The number of protons that are in the nucleus. This is what identifies the elements. It's the protons that change the element. Different elements, atoms of different elements can lose and gain electrons and still stay that same element. If we change the protons, we change the element. If you look at that bottom number on the periodic table, that goes up in order. So lithium is 3, beryllium is 4, boron is 5. We're just increasing each time. So when we when we change the number of protons, that's when we're changing what element that is. So the atomic of the proton number, atoms have no overall charge. So this bottom number tells us the number of protons, and it's equal to the number of electrons. Okay, so let's take an example of lithium, for example. Mass number 7, proton number of 3. A quick reminder of protons, electrons, and neutrons. Protons, we're simply looking at that bottom number, therefore we must have 3. Electrons is the same because atoms have no overall charge. When we're talking about charged particles, we refer to them as ions. So atoms have got no overall charge. They've got to have the same number of positive protons and negative electrons to cancel out that charge. And neutrons, then, we know that we've got 3 protons, so plus a certain amount of protons will equal that top number. So 3 plus something equals 7. So therefore, we've got 4 neutrons in that. Okay. If we just go for one more example, so we think of if we think of bromine. So bromine is 79 and 35. So proton, it's that bottom number that we're looking for the protons. So we've got 35. Going to have the same amount of electrons because atoms have no overall charge. And the 79 minus the 35 protons to give us 44 neutrons. Okay. So an ion then. So an ion is a charged particle. So when a atom loses or gains electrons, we then refer to it as an ion. Okay. So let's just note that down. The atoms form ions by gaining or losing electrons. Okay. Now they have different number of a different number charge, so different charge value depending on how many electrons they've either lost or gained. Okay, and I'll give you a couple of examples of that. So if we think of bromine, for example, okay, so bromine is a non-metal. And our non-metals accept electrons. Okay, so they're going to gain electrons. So our bromine will become Br minus. It's in group 7. It's got the capability, the space to accept one more electron into that shell. Accepts the electron, therefore becomes minus, because what we've got now, if we think about our protons, neutrons, and electrons again. So if I just pop those numbers back onto one of the examples we looked at, so bottom number is 35. Okay, so we've got 35 protons. So that's our 35 positive charges. And as the atom, it's got 35 electrons. Okay, but now it's accepted an electron. We've now got 36 electrons. Okay, so we've got 36 negative charges, and therefore we've got that overall negative charge. Our metals, so let's take magnesium, for example. They accept electrons. Okay, so magnesium is in group 2. It's got 2 electrons in that outer energy level, and therefore it wants to sort of get rid of those. Okay, and so when they lose them, they're going to become positive ions. Okay, so magnesium is 24 and 12. It will become Mg2 plus because it originally has 12 protons, 12 electrons, but it's lost 2 electrons, so it goes down to having 10 electrons. So 12 positive charges, 10 negative charges, and therefore becomes that 2 plus ion. Okay. Okay, isotopes then. So the reason that we have masses, so chlorine, for example, when you look on the periodic table, its mass is 35.5. Obviously, we haven't got half a neutron or anything like that. That is showing us that we've got an average of the isotopes. We've taken an average of the isotopic masses. Okay. Now, when we refer to these ions, we will talk about them as like chlorine 35 and chlorine 37. So that we know which one that we're talking about. So isotopes have the same number of protons, but different neutrons. Remember that the proton is what defines the element. So same number of protons, different neutrons. And the neutrons have got a mass. Remember in that little table, we've got a mass of 1. And therefore, it's going to change that mass, but it's not going to change the element because we're not changing the protons. We've got the same protons. Okay, so if you just were to do, like you've probably done plenty of times before, protons, electrons, neutrons, bottom number 17, 17, 35 minus the 17 to get our neutrons. So in chlorine 35, we've got 18 neutrons. And if we repeat the same process, still got 17 protons, 17 electrons. So our element doesn't change because we've got the same protons. However, this time, because we're 37, we've got 20 neutrons. So in terms of sort of chemical and physical properties, because they've got the same protons, okay, it doesn't change their physical properties because it's the same element. So if you had 2 samples of different isotopes, they would look exactly the same. They would react exactly the same because they've got the same electrons, and it's that electron structure that denotes its reactivity, etc. The only difference would be is that it would have a different mass. Yes, if you had 2 samples and you put them on 2 scales, you get that slightly different mass, and that is the only thing that it does affect. Okay, so your electrons define your chemical properties, so they've got the same electrons, so they react the same way. Protons is what defines your element, so they're the same thing because we've got the same number of protons. We've just got that slight change in mass. Okay, so in your little work pack now you will find a couple of different questions. So if you want to hit pause on the video, have a go at those questions, and then check back in and I'll go through the answers and the mark scheme with you. Okay, so I've put the mark schemes in as well, so that we can look at, you're getting that overview of all the kind of different ways you can answer it. So this one, your first one, define relative atomic mass. There's lots of definitions to learn in chemistry, and as you move through the course, we'll talk about more definitions that you need to learn. Just learn a way that works for you. Learn what feels right, what sort of flows, off your tongue, to define it. Because if we look here, you can see that there's lots of different ways that you could define relative atomic mass. So just find one that works for you, one that flows, and just parrot fashion learn it, because it's two quick, easy marks. So when you're looking at these, we're looking for something about the average or the mean mass of the atoms of an element. And then we're looking for what's underneath compared to the mass of one atom of carbon-12. Yeah, so there's lots of variations. So I'll just let you decide which one you're going to choose. Just pick one that kind of, that just works for you. Everybody will pick it slightly different. So if you pop back to it then, in terms of fundamental particles, state the difference between an isotope of an element. Okay, so we've got different number of neutrons, same electrons. Okay, so that's what the two things that we're looking for. If you've said the same protons and electrons, that's absolutely fine. It's just that it's the electron part that gets you the mark. Okay, so different neutrons, same protons and electrons, or if you just put same electrons, that is fine. So different neutrons for the first mark and the same electrons for the second mark. Okay, state why isotopes of an element have the same chemical properties, because they've got the same number of electrons. Electrons define its chemical reactivity, protons define what element it is, and our neutrons simply just change the mass of those. Okay, these little tables, just quick wins, quick, easy little marks. Mass of a proton, 1, relative charge, +1, electron is -1. The only difference now is we need to try to remember to put that it's 1/2000. Number of neutrons and electrons, so it's given us two different elements, and we've got the number of protons. Remember, that's our bottom number. So the number of neutrons is top number, take away bottom. So we've got 46 minus 22. I'm just going to pop that in my calculator. You can use calculator for your exams. Obviously, you can have some more complicated calculations to do when we look at amounts of substance. You can use your calculator in your chemistry exam. It is absolutely fine. Oops, helps if I put minus rather than divide. So I've got 24 neutrons. Okay. Remember, looking at the bottom number, electrons has to be the same. So I've got 22 electrons. With this, I've now got a different, so I've got an isotope because I've got a different mass. The mass number is 49 this time. Take away your 22 protons. So it's got 27 neutrons. And we've also got a +2 charge. So we're an ion. So because we're +2, we've lost 2 electrons because we've now got more protons. So if we've lost 2 electrons, if we work out what we would have had, so we would have had 22, but we've lost 2, therefore we've got 20 electrons. Okay, and there's your little table of answers. So again, just another example, we've got magnesium that's got 3 isotopes. In terms of subatomic particles, state the difference between the 3 isotopes of magnesium. Yeah, you can simply say they've just got different number of neutrons. If you've worked it out and you've said that magnesium 24 has got 12 neutrons, 25 has got 30 neutrons, that's okay. Just simply saying they have a different number of neutrons is absolutely fine. And the second part of that question, state, if at all, the chemical properties, how the chemical properties, sorry, of these differ. Well, it doesn't, because they've got the same electrons. Okay, right. So what we've got, if you just look with a little bit more practice, there are some few more practice questions here. And on the next slide, I have put the answers, so I'll quickly flick it on so that you can pause this video and use the answers as a mark scheme if you wish to have that little bit more practice. Okay, so there are the answers. Right, let's have a look then at the atomic models. So remember that Dalton was about that we had this solid, indivisible sphere. So like a marble, a ball bearing or something, you know, you've got that solid model. However, when we discovered electrons, Thomson discovered the electrons, and therefore we had to change our idea about this, because we now knew that we've got these electrons as well. So it moved on. So this has been sort of termed, oh, where's my pen gone? It's here. This was sort of termed the plum pudding model, because it kind of went to the fact that it was a ball of like positive charge with those electrons dotted in it. Yeah, so it's kind of nicknamed the plum pudding model, as a plum pudding would have been, apparently. So it was the discovery of the electrons that we changed the idea into this plum pudding model. So Rutherford, he was the one that did the alpha scattering and discovered that there was empty space, etc., within in an atom. So he fired alpha particles at a very thin, or just one atom thick layer of a gold sheet. And what he saw, that most of the alpha particles passed through. So therefore, because most of them passed through, the atom must have been mainly empty space. Some of them were kind of deflected, so we knew that the electrons must be kind of around there, deflecting those off. So we got most of them straight through, some with a bit of deflection, and very few that were deflected straight back, almost as like they've been repelled back. Because the alpha particles, remember, alpha particles are 2 protons and 2 neutrons. So we've got that positive charge. So as that positive charge hits that nucleus, we get very few bouncing straight back. Yeah, because we've got that small, dense nucleus. So we changed the idea that we now needed this empty space within it. The nucleus was very dense. Still wasn't sure about protons and neutrons, just knew that it was that positive charge. So we've now got really small, dense, positive nucleus and electrons sort of dotted around. And that actually it wasn't sort of a ball of dough with those electrons dotted in. It was empty space. Okay, so that's how we changed that idea and that model. And then we're pretty much where we are today. So Bohr's model, that was just about putting the electrons into those shells rather than just that random dotting around. So into our energy levels, like you will have looked at GCSE, etc. And knowing that they were in there. So electrons were in these fixed orbits, not just sort of anywhere dotted around. Each shell had got a fixed energy, and those electrons could move between the shells. So we know that if radiation is absorbed, they can jump up a level, they can move back down a level and then emit that radiation. Okay. So yeah, this is pretty much where we're at now. Okay. Obviously, we've also discovered as well that we have neutrons. So we know that nucleus is made up of the protons and the neutrons. But in terms of electrons, it was Bohr that, you know, said they were in these fixed energy levels and had these specific energies. Okay. Right, so again, just a couple of questions, a couple of quick questions asking you about the atomic models, how we've changed it, etc. So again, if you want to hit pause on the video, have a go at those questions, check back, and we'll go through the answers and the mark scheme. Okay, so this first question then, so we've got the model proposed by Rutherford. So we've got that positive nucleus rather than that sort of kind of like dough or that pudding. I was going to say pie. It was a plum pie model, was it? Pudding model. But rather than it being a, you know, sort of like a ball of dough and there was electrons dotted about, we know that we've got this positive nucleus. It was small and compact because most of the alpha particles went straight through, so we know that it must be mainly empty space. So two features of the current model that are not shown in Rutherford's model. So feature 1 and feature 2. Okay, so the current model, we have neutrons and protons. Rutherford's model, we were still just at the point of having that positive nucleus. Yeah, we didn't know about the neutrons yet. And in our current model, we now know that those electrons are in those different energy levels. If we look back and we think about Rutherford's model, they were just sort of dotted around, not really in those very specific energy levels like we have today. Okay, so I'll just pop back to that. If you identified that, you know, that first energy level should have only had 2 electrons in, whereas in the diagram it had 3, that is perfectly fine, because you're absolutely right that there's 2 in that first one. Okay, and then our second little question we've got here, so we've got J.J. Thompson discovered the electron, so he suggested that the negative electrons were just kind of dotted around in this positive charge. And again, 2 differences between the Plum pudding model and the atomic structure that we use today. Okay, so various things you could have said. That the nucleus contains the protons and the neutrons, or that we've got a central nucleus. It's not like one big nucleus and then the electrons dotted around the outside. And again, about now that we have those electrons in those specific energy levels. Okay. Right then, hope you found that session useful, and I'll see you in the next session. So nice and straightforward for this one, just recapping that knowledge and just building it up slightly. I'll see you next time.